exercise 6 of problem set 1. And here I have to compute a lot of things: adjacency matrix, degree distribution, average degree, density, shortest path lengths. Well, they say shortest paths for every pair of nodes, but I think it's shortest path lengths, okay? Diameter, and average and global clustering. And they give me a few networks, okay? I want to do this exercise with this small network, and this is because this is related to the clustering, okay? So here I want you to explain the formula for the clustering, so we can understand it a little bit better, okay? So let's see. So I'm going to do this with this network, okay? So the adjacency matrix, it's a 3x3 matrix, which is 0, 1, 1. You can see that all nodes are connected between them. So I have 1, 0, 1, and 1, 1, 0. So this is the adjacency matrix. This is easy. The degree distribution, that's simple too, because the degree distribution is, okay, pk is going to be delta k2, because this is a delta Kronecker, okay? This is a delta Kronecker. I think it's written like this. So it means that it's going to be, in this case, because I have the 2, because, okay, so this is a comma in here separating both numbers. So it's going to be 1 if k is equal to 2 and 0 otherwise. Okay, so that's the idea. So we have that since all nodes have degree 2, then this is what we obtain. Remember that that this degree distribution can be obtained just by doing the addition by rows here, okay? Also, the average degree, well, the average degree, since all the nodes have degree 2, then the average degree is going to be equal to 2. That's quite simple too. Density. Okay, since we have all the possible links here in this network, then the density is equal to 1. And the shortest path length, well, since all nodes are connected to all other nodes, then we have that the shortest path length is going to be dij is going to be equal to 1 for all I different from j. Okay, so that's going to be the shortest path distribution, and the diameter is going to be equal to 1 because all these numbers are equal to 1. And now for the clustering, which is the one that I wanted to show. The clustering, remember that is, we can compute the average, the clustering for each of the nodes, but since this is a symmetric network in the sense that all the nodes are equivalent, because the relation between, if I change the labels of these nodes, the result in every aspect is going to be exactly the same, because all nodes are connected to all other nodes. So in this case, remember that is the number of triangles where I is a vertex divided by the number of possible triangles. Where I is a vertex, okay? Remember that that's the idea. In this case, since all nodes are connected to all nodes, we have that for node 1, for instance, if we pick node 1, then we see that it has 2 neighbors, and these 2 neighbors are connected between them. So in this case, we have that the number of triangles connected is 1, and also the possible number of triangles is 1. So we have that the clustering of node 1 is 1. But this is the case for all nodes, okay? So this is, the clustering is for I equal to 1, 2, and 3. So that's for all the nodes. And for the global clustering, remember that we have 3 times the number of triangles divided by the number of triplets. Okay. The number of triplets is given by the degree of each node. So if this is node I, okay? So if I go from here and I have some degree Ki, remember that the number of triplets is going to be Ki over 2, okay? The binomial number, which is Ki times Ki minus 1 divided by 2. Remember this. And these 3 disappears because I'm going to count each of these. When I do this addition from in each of the nodes of this, okay, using this formula, what is going to happen is that I'm going to count 3 times every triangle. Okay, so in our case, if we are having this problem, okay, this network, so in our case, if this is node 1, node 2, and node 3. If this is node 1, then I'm going to count 1 for this case, okay, so this is going to be 2 times 1 divided by 2, so I'm going to count 1 for this node, then I'm going to count also 1 for this node, and I'm also going to count 1 for this node, but I have only one triangle. So I have to add this, I have to multiply by 3 in the numerator so that I have the number of triangles is so I can normalize, because the clustering it's supposed to be 1 when all triangles are formed, okay? So that's the idea, that in a clique the clustering coefficient has to be always equal to 1 when we have that all nodes are connected to all other nodes. And that is why I write this 3 here, okay? I have to multiply by 3, because if not, then I would have 1/3, and that's not the case, okay? So I have 3 over 3, which is equal to 1, and so the clustering is okay. And this is why I wanted you to use this formula. By the way, the formula that it's in the notes is not right. I'm going to correct it, okay? It should be something like this. I mean, this formula is okay, this is right, but the one that is not okay is the other one, the one with a trace, okay? So it's 1 over 2 times the summatory of ij, a, ik, a, jk. So this 1/2 is missing, okay? Divided by 1/2 over this summatory also, okay? So that's the idea. So in the end, these two cancel out, and what I find is that this is the trace of a to the power of 3 divided by this thing over here. So the formula is not right in the notes. I will correct it and upload them, okay? So that's what I'm going to do this week, okay? And this is the formula that you should use if you want to do it with a computer. If not, just count the number of triangles and the number of triplets.